We're about a minute early.
Matt dropped the class.
I dropped him for. I just didn't like him. Okay, so just a summary, because I know we took a test and it's been a while. We're talking about series, infinite series, right? And right now we really have only covered 3 different types of series. We have geometric, right, which has 2 forms. And I handed you today a summary. Okay, this is a very important sheet of paper. I'd keep this. I'd hang on to it even if after you're done with this class. And notice that the second row there says geometric series, and this sheet only has one of the 2 forms, right? It has this one. But just keep in mind that this is an equivalent form. If you start at n is 0 instead of 1, and change this to n instead of n minus 1. So if you want, you can add that right above the other one. All right, so we know that this will converge if the absolute value of r is less than 1 and diverge otherwise, right? So we know we can handle those things. And the main thing we look for in geometric series is a number raised to a power, and that power keeps changing, right? So the n appears in the exponent. Then we have telescopic. Now we're going to start today's class with the telescopic because I didn't really get into that. We only did one example. So I'm going to do a telescopic today. And then we talked about harmonic. In harmonic, we said all harmonic series diverge. And the format is that you have a sum, n starts somewhere, that's a question mark, and then goes to infinity. You just have some constant over a linear function in n. In other words, this is a linear expression down here with n in it. And if we have that, then it's going to diverge. All right? So of these series, okay, of the series that we know so far, geometric and telescopic fall into a category of series that we can actually find the sum, right? Like a geometric series, if the absolute value of r is less than 1, we know that it actually converges to this number. So we can get an answer, right? Telescopic, they sometimes converge, sometimes diverge. If they converge, we can find the sum. But there's not a formula like the one up here that I can give you. So what I'm getting at, okay, is that there are only 2 types of series that we can find the actual sum of. With me? From here on out, we will not be able to find the actual sums of these series. All we will be interested in is whether or not they converge or diverge. That's all we are going to want to know. All right? Yes?
In further math classes, will we be able to find it?
There's no general formula to figure out when a general series or what it converges to. All right? Later on, I'm going to do a bonus lecture at the end of. I decided I'm going to do it. I don't know if it'll be a bonus. I can't say that yet. But I'm going to offer a lecture where you can come in, optional, and I will show you a particular series and what it converges to. We'll find the sum, and then once you see what it takes to get to it, you'll appreciate the fact that it's not easy. And so, so the answer is no. There's not like a simple way to do it later. But it turns out that all that's important to us is whether or not it converges or diverges. Because if you back up and you think about where this all came from, this whole chapter, remember we had these functions. I put them up on the board and I said, hey, does this line approximate that sine curve? No. And then I said, does this parabola? Oh, it was better. And then remember that? And I just kept on showing you more and more, and it got better and better and better. That series of functions that I showed you converged, all right? And that's what we want to know, is whether or not something will converge or diverge. All right, so let's start today's class with a harmonic series, just to get us warmed up. And it's been a while, but like I said, we only did one of these. Okay, let's do this. Let's do sum n equals 1 to infinity of the arctangent of n plus 1 minus arctangent of n. That looks pretty ugly, right, with all that arctan stuff in there? So we could start writing this series out, right? It would be, let's just start plugging it. Oh, I should say that's not geometric, right? It's not a geometric series. It's not harmonic, right? Is that obvious? Yes? Okay, so we can throw those out. So since I don't know what it is, well, I know it's telescopic, but let's act like we don't. This would be arctan of 2, right? Whatever that is, and I'm not getting my calculator out. Minus arctan of 1, right? That would be that's what I get when I plug in 1. And then I say plus, now what? Arctan of 3 minus arctan of 2, and then I keep doing this, right? And do you see now that we're going to get some cancellation?
Yes.
Okay, is this starting to ring a bell a little bit? Oh, man. Okay, so I'm going to start getting cancellation. As soon as you see this cancellation is going to take place, you start thinking telescopic, all right? That's what you start thinking. This might be telescopic. So the proper way to do telescopic, and again, it's been a week since we've done this, is to look at the nth partial sum and then take the limit as n goes to infinity after you have a formula for it. So let's look at the nth partial sum. So that's going to be first plugging in 1, which we did earlier. And then plus, now plug in 2. And you keep doing that, right? But this time you stop. And the last one out here would be what we get when we plug in n, right? That's what this means. Sum starting at 1, but stopping at n. So what would happen if I plug n into that expression? Get arctan n plus 1 minus arctan of n, right? Wouldn't that be the last one? Okay, so this is what I'm getting if I plug in n. What about the one that's right before it? That's what I get when I plug in what? N minus 1? One less than this? So that would be arctan of what? N minus arctan of n minus 1. Understand? And then I have more stuff in front of it and a bunch of stuff in between, right? Does this ring a bell? Yeah. We're going to try and find a pattern of how they cancel. All right, so this first one here, does it get canceled with anything? Yeah. Yes. Now, I also want to do something else. I want to separate. That's what I got when I plugged in 1. This is what I got when I plugged in 2. This is what I got when I plugged in n minus 1, and this is what I got when I plugged in n, right? So it's this clump of stuff, right? All right, so this one right here will get canceled out, right, by this one right here, which is 1 away. Okay, so I'm looking at this as being, this whole thing as being one expression. This one is the next one, right? So the first guy in this one gets killed by the second guy in this one. So first ones kill off second ones to the right. Yes? First ones kill off second ones to the right. So let's look at all the first ones. This first one right here should kill off the second one and the next one. So it should go, right? Yeah. And then that keeps happening. How about this first one? This first one kills off the second one over here, so that's gone. Understand?
Yeah.
The last first one I have is this one. This first one, does it kill off? No. This one stays. So I'm going to box this. This guy does not get killed off. It's still here, right? Now that was me looking at all the first ones, right? Now let's look at the second ones. Yes?
And that last one stays because that's where it ends, right? The series.
Yeah, this one stays because I stopped at n, right? Because it's a partial sum. There's no second one on this side over here to kill off with it, right? To cancel it out. So that was me starting with the first ones and looking for the second one over there, right? Look at the first one, look for the second one over here. First one, look for the second one over here. Now let's do the opposite. Let's go and look at the second ones and see if there's a first one in front of it. So what about this one right here? Is there a first one that's going to kill that off? No. So this one stays also, doesn't it? How about this second one? Well, it got killed, right? Okay. How about this second one? Is there going to be something over there to kill it off? Yes, somewhere in this dot, 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 right? It's going to get killed off. Okay. And then this second one? It did. It got killed off by that one, right? Yes. So the only thing that still remains is what's in those boxes. Do you agree? You'll agree? What's that?
Why wouldn't down?
Okay, so think about the pattern. First ones cancel the second one to the right of it, right? Or you can look at it another way. Second ones get killed off by first ones in front of it. Second one gets killed off by first ones in front of it, but there is no first one in front of it, right?
That makes sense.
Got it?
Looking at it the other way, I couldn't understand it.
Everyone on the same page here? So S sub n, I could write it as, after everything cancels out, I just have the negative arctan of 1, and then down there plus arctan of n plus 1. Is it hot in here? Feels stuffy or something. Y'all agree?
Yes.
All right, so that's why we call this telescopic. What was the other name for this? Telescopic collapsing, right? So everything collapsed out except for like some stuff at the edges. All right, so if we want to know what this sum is up here, remember the definition of this, if this actually goes to a number, if it does, then this will be equal to the limit as n goes to infinity of S sub n. That was the definition of the sum of an infinite series. So I just need to take the limit of this and let n go to infinity. So the limit as n goes to infinity of this expression, negative arctan of 1 plus arctan of n plus 1 equals. All right, so let n go to infinity. This doesn't have an n in it, right? What is arctan 1? Pi over 4. Pi over 4. And then they have we have a negative in front, right? So negative pi over 4? How'd you get that?
The square root the unit circle.
So you're thinking unit circle? Unit circle?
I always think the unit circle.
Okay. Yeah, all we're doing when we say arctan of 1 is we're saying where on the unit circle is tangent 1, but that means your y and your x coordinates have to be the same. Tangent is sine over cosine, so that happens here. It also happens in the other quadrant down here, doesn't it? But arctan is restricted,
Yes.
so we don't look there. All right, now let's let n go to infinity here. N plus 1 would become infinite, right? What's arctan of infinity?
Pi over 2.
Pi over 2. Now that one I think comes better if you look at the actual tangent function. When you graph tangent, right, this is tan. I'll say tan x. If you're saying arctangent of infinity, you're really saying where is tangent infinite? And that happens right here at this asymptote, right? And that happens at pi over 2. With me? So we get this plus pi over 2. And you can put those together, common denominator, you should get pi over 4, positive pi over 4. So this telescopic series converges to pi over 4. What's wrong?
Doesn't that go to 0? Because if you get a common denominator, you get
2 and 4?
So we-
This is a negative 1 pi. Am I missing something?
Oh, okay. Negative 1 plus 2 is 1.
Yeah.
Okay.
Okay. It's all right.
It's been like
Okay, we good? We good? Yes? Okay, so I would make sure you watch the homework videos over this. I do the problems in the book, the ones that I assigned for homework out of 8-2, numbers 25, 26, 27, 28. They all have kind of different algebra required to do them. On your test, your next exam, I did not give you one of these on your last one, right? So on your final, you'll probably have one of these, and I'm looking for correct setup on these. I'm looking for you to identify that it is going to start having cancellation. Go, yeah, that looks like it's going to cancel. Then writing S sub n and looking at what it is, showing you're canceling, then limit of that, and figure out what it is. All right?
Can you explain one more time the n plus 1 or tangent?
Okay, this.
How did you get pi over 2? Or
Okay, let me do it this way. What is tangent of pi over 2? Well, if you go to the tangent function, you graph it, right? This is pi over 2 right here. It's undefined because you have vertical asymptote. But as you approach pi over 2, right, it approaches infinity. Got it? So this is actually, I know this is not correct, but this is basically approaching infinity, all right? So if I now come in and I say, what's arctan on this side? I know this is a terrible way to do this, but what's arctan of this side? Arctan of tan, this is just pi over 2. They cancel each other out, right? And this side says arctan of infinity. So arctan of infinity is pi over 2. See, when you let n go to infinity, this right here becomes infinite.
gotcha. Okay.
Yeah?
Yeah.
Okay. Were you missing the n going to infinity?
Yeah.
Oh, okay.
That's
Yeah.
where I was-
All right. All right. Okay. Yeah, don't forget this isn't a limit, right?
Because it's the end.
That's right. All right, that's it. Everyone have one of these? There any extras? Yours all wet.
Yeah.
Here, you want that towel?
The table's wet too.
Oh, that would have been super bad news.
There's more over there. Okay. Let's take a look at this. I want to address the first test that's on here. This is a summary of convergence and divergence tests for series. These are all the different tests that we have. The first one, the nth term test, is a very nice test, but it only tests for divergence. Sometimes it's actually called the divergence test. So the way it works is you have a series. You look at just the sequence inside. If this sequence does not go to 0, automatically that series diverges. That's what that says. Do you see that? Diverges if the limit as n goes to infinity of a sub n, if that does not go to 0, then divergence. You're done. All right? If it goes to 0, you don't know anything. Okay?
It just converged, we didn't know what to do.
No.
No?
It could diverge still. We did this. We looked at two examples. I don't know. Well, I don't think I showed you that one. This is harmonic, right? It diverges. This is not harmonic. I'll do this one instead. Look at these pieces inside here. If n goes to infinity, that goes to 0, right?
Yep.
If n goes to infinity here, that goes to 0 also. Because 1/4 to bigger powers gets smaller. These both go to 0, don't they? This diverges, but the sum diverges because it's harmonic. This one converges because it's
P is less than 1.
R is less than.
R is less. So this is what type of series? No.
Geometric.
The sequence is a P, right? You're confusing. No. Yeah, you're confusing it with a P series. It's not a P series. We haven't talked about P series because,
No, I looked
you see?
I switched that.
What type of series is this? Geometric. That's a geometric series. That's going to converge. This one diverges. But notice both of the sequences, not the sums, both the sequences go to 0. So if the sequence goes to 0, you don't know. It could converge, it could diverge. But if the sequence does not go to 0, it diverges automatically. Okay? We always want to be able to run that test to start things off. All right? But now we're going to talk about geometric. We're done. We've already done that. The next one is called P series. And this is what a P series looks like. Notice that this is not a geometric series. What's the big difference between this and a geometric series?
The N and the P are switched.
Yeah, the n down here, the n is in the base instead of the exponent. And then P here is just some number. If P is greater than, right, or equal to, no, greater than 1, this will converge. If P is less than or equal to 1, it will diverge.
Are we about to have this paper on the next exam?
I haven't decided. I didn't get it on my exam when I was in Cal 2.
You seem so much more fair than me.
Yeah. All right, so let's do some examples of the P series. Look, the P series, it's a simple series. It's just a matter of do you recognize it, all right? So here's an example of a P series. Sum n equals 1 to infinity of 1 over n squared. That is a P series?
Yep.
Okay, what's P?
2.
This is a P series. P is equal to 2, which is greater than 1. Therefore, this series converges. Done. That's it. You're done.
So we don't have to figure out what it does too.
You don't have to do anything on that. Okay?
That's awesome.
No, P series it's just a matter of identification. All right? Now, we're going to use this in a different way in a little while. But, all right, so what if I had put up here, like 10,000 over n squared? It wouldn't matter. This is still a P series. And that's because if we have a constant inside of a series, we can bring the constant out. And I'm going to give you those properties in just a second. But if we bring the constant out, we'd have 1 over n squared. That still is going to, what, converge to a number? And if it converges to a number times 10,000, it's still a number.
The same if it's at the bottom too, right? Let's say it's 10.
That's right. If it was at the bottom, let's just make it 10 instead of a 10,000. Then what I could do is I could pull out a 1/10, and then, see, it's the same thing. Okay, so here's another one. What about if we have sum n equals 1 to infinity of 4 over pi times the square root of n. I need to start throwing away some of these markers.
It's 1/2.
This diverges y.
It converges.
Converges y.
Yeah, it's less than.
Okay, so for now, even though I haven't put this on the board yet as a formal property, let's take the constant out of the series. You can only take constants out. It's like integrals. Remember, with integrals, you couldn't pull functions out, but you can pull constants out. And then this is 1 over square root of n is n to the 1/2. And now you say, that's a P series, right? And my P here is a half. And that is less than 1. In the case that it's less than 1, it diverges. So therefore, the series diverges. Those are pretty straightforward, right? Pretty straightforward? Let's give you some of the properties. Where the heck are they?
Do they work like logs? The properties?
No, it's not like that. Not that many properties. I thought I had them right here. Oh well. Well, I'll just put it up here. Some properties. Of convergent series. I'm going to underline the word convergent. We need these series to be convergent for these properties to hold. So here we go. Suppose, this is the symbol for suppose. Suppose the sum n equals 1 to infinity of a sub n and the sum n equals 1 to infinity of b sub n both converge and c is a real number. A real number. I'm using that for number, not hashtag, right? Good? All right, so someone gives us two convergent series, right? That's what we have. Then this is what's true. The sum n equals 1 to infinity of c times a sub n equals c times sum n equals 1 to infinity of a sub n. What is that property telling us we can do? We can pull constants out of series as long as they converge. All right? Now, it turns out if they diverge, you can do that also. But the next property you can only do with convergent series. So let's call this the first property. I'll just put a 1 next to this. The second one is that the sum n equals 1 to infinity of a sub n plus or minus b sub n is equal to the sum n equals 1 to infinity of a sub n plus or minus the sum n equals 1 to infinity of b sub n. You can take them apart. We also had this with integrals, right? You could split an integral up into two integrals as long as there was addition or subtraction between the terms. Same thing here. I will also point out for those of you who may not be familiar with this, whenever you see plus over minus like this in a formula, and then you see it again over here, it corresponds. So if this was plus, then over here it's plus because they're both on top. This is minus, it corresponds to the minus over here. There are some formulas, there's one in pre-cal for cosine, sum of angles and cosine, where it's opposite. This says plus or minus, but in the formula it's minus over plus. It's not because they just did it backwards. It's because if this is plus, then in the new formula over here on this side it's minus. And if it's minus, then over here it's plus. So there is some method in that. Tops match, bottoms match. Understand? Okay, so this is just a formal me telling you, look, you're allowed to pull constants out and you're allowed to split series up into two series so long as they were convergent to begin with. That could get us into trouble sometimes. All right, here we go. What's the next thing on our list? The next test is called the integral test. This is the first test that actually requires quite a bit of thinking, okay? So here's what the test says. Let's say that you have some infinite series, okay? And you want to know if it converges or diverges, right? What we're going to do is we're going to define a function f of n to be a sub n. So you might remember this when we were first doing limits of sequences, and I said you couldn't do L'Hopital's rule unless you switch n over to x. Okay, this is kind of the same thing, except we're not switching n over to x. We're just going to say that that sequence is a function. All right, it's a function of n, and we're going to leave n as just being n. Right? We're not switching it to x. It says this. What are the conclusions of this test? 1. If the integral from 1 to infinity of f of x dx converges, I'm going to put a little if here. If this integral converges, then the series converges. What does part 2 say? I mean, this is all in your table, but I don't know why I'm writing it up here. Just, I think it flows better when I write it. The second part says what? If this integral diverges, this series diverges. In other words, whatever the integral does, this series does. Okay? That's the integral test. Before we get to the next part, which is the conditions, on the comments on the right-hand side, I want to just kind of show you visually what's going on. If I take a sequence, right? It's a bunch of dots. If I now look at that sequence as a function of x, then that would be everything, including all the stuff between the dots, wouldn't it? Yes? If I do an integral from 1 to infinity, it's giving me the area underneath this, right? Yeah. When I do a series, I'm not finding an area, I'm finding the heights of all of these points, right? And I'm adding them up. So like, let's say that's 2, and this is 1, and that's a half, and that's a fourth, or something like that. I'm just adding those heights together, right? Would you agree that the integral, the area, is bigger than the heights of those points added up? Do you agree with that? So if this area is finite, if it converges, then our sequence should also converge. That's the idea. All right? But we'll just take it on faith that it works. Is that all right? If that's the best I'm going to be able to do for you right now? But there are some very strong conditions that you need in order to use this test. And what are they? They're in the comments. Okay. F must be continuous. F must be positive. F must be decreasing. And integrable. Same, you can say it either way. So the function that we create from this sequence has to be a continuous function. It must always be positive, and it must be decreasing. Now I'm going to add something to this that the sheet doesn't say. This positive part and this decreasing part both must happen eventually. Eventually, meaning maybe in the very beginning it's not positive, maybe in the very beginning it's not decreasing, but eventually it stays positive and continues to decrease. All right, I think the best way to illustrate this is to do an example. Yes? No, because we have to have our sequence has to go to 0, right? Because if our sequence doesn't go to 0, it diverges automatically. So that's part of why it has to decrease. It has to be positive because if I'm comparing this to an integral, I want my area to be positive, right? Because we've seen in integrals where if your area is both positive and negative, they start to cancel each other and it gets kind of weird. So This test will only work if we can guarantee that this thing stays above the x-axis and is going down. Okay? Is that good enough?
Sure.
Okay. All right, so let's do an example. Let's do this sum. This is an example. N over n squared plus 4. So now we're starting to get more methods here. So you want to be a little systematic with this. The first thing I'm going to do on this is what's called the nth term test. What test is that on your sheet? The very first one. So I'm going to take the limit as n goes to infinity of n over n squared plus 4. And when I do that, I get infinity over infinity. So I do a quick L'Hopital. Yes, you have to switch to x and all that stuff, but I know I could. What would I get?
0.
I would get 0 when I take this limit, right? Everyone okay with that? So we get 0. What does that tell me? Nothing. Test fails. Right, so I still don't know what's going on, right? Is this a geometric series?
No. Oh, it could be.
Well, could it be? What do you need for a geometric series? Where does the n need to be? In the exponent. You don't see an n in the exponent, do you? So it's not geometric. Telescopic. We would need things to cancel each other out, right? And I don't think you're going to be able to do that. I need you to do your homework, though, because there is a problem that's very similar to this, where if I change that to a minus, you can probably do telescopic on it, because you break down the bottom, then you do partial fractions. Watch the homework. Watch the homework, all right? But this one, not telescopic. Is it harmonic? No, because you need constant over linear. You don't have that, right? Is it a p-series? Is it a p-series, though?
N is greater than 1.
No.
So it converges.
N is greater than 1?
If you do the n squared, well, yeah, there's
N plus 4.
Yes, okay, I agree you have an n squared here, but you have an n on top, and for a p-series it must be constant over n to a power. And this is not a constant over n to a power, so it's not a p-series.
Even with that plus 4, if it was 1 over, it still works.
If it was what?
If it was 1 over,
The n
If it was 1 over n squared plus 4, hang tight. Okay? That still would not fall into the category of a p-series, though, because it has to be 1 over n to the p, nothing else, or constant over n to the p. All right, so everything that we've looked at, this is something different, right? Maybe integral test? Well, if it's integral test, I need to be able to rewrite this as a function, n over n squared plus 4, right? And right away, I need to think about this as an integral. I need to check to make sure f is what? Continuous. It is positive, and it is decreasing, and it is integrable, right? All these things I have to check. But before I do that, is this even something I want to integrate? So think about what this integral is that you would be doing in this test. It would go from 1 to infinity. These are improper integrals. It would be that with x's, x over x squared plus 4. Could you integrate that? How? Basic u sub, right? The whole denominator would be u. Derivative of that, 2x, it's up top, you're off by a little bit. You could integrate that, right? So since you can integrate that, I would encourage you to continue moving forward with this method, all right? If this turns out to be something that you can't integrate, don't even bother with this method, right? Okay, so we're happy with that? All right, the biggest mistake I see students make using the integral test is they do exactly what I've done on the board. This, they compute the integral, and that's it. They forget to check all the things that it has to satisfy. This must be part of your answer, all right? So here we go. Is f continuous? Yes. Why? Because what? The numerator is n. N is a continuous function. because it's a polynomial. N squared plus 4 is a polynomial. Polynomial divided by a polynomial is continuous, or a continuous function over a continuous function is continuous on its implied domain, meaning as long as this denominator is never 0, we're good. It's never 0, right? So we are good, it's continuous. Okay, next. Is f, what's the next thing? Positive? That just means what? Is f of n greater than 0? Question mark.
Yes.
Okay, why? How can you convince me of that?
Even if all negatives will go to positive and 0 plus 4.
The top is n, right? And what are you going to start n at? 1? So that's always a positive number, right? N squared plus 4 is always positive. Even if you let n be negative, that would still be positive, right? So you have a positive over a positive over a positive. That's just me saying I have a positive number over a positive number, which is positive, which is greater than 0. Check. I've done that part, right? This must be written down. Yes?
One small question. You said n is going to start at 1, and we should let n squared be anything we want, so we can have n be multiple terms at 1.
No. I was just stating that, like not only is this positive for n being 1 and on, but this would have held for any n, right? Okay. Yeah, but we're not changing n to anything else. All right, one more thing to show, right? That f is decreasing. So is f decreasing? Yes? Why?
It's growing faster than the numerator.
It is, but that doesn't suffice.
Because it would be like 2 over.
How do we show things decrease? We did this. Remember what this was at the end of a section? I said show something is monotonic.
Oh, you would flip it.
This is what we're talking about. No, that's bounded.
Oh, my bad.
We're not looking for bounded. We're looking for monotonic. Okay, so to show this, you have to must show that a sub n is decreasing. Less than? Greater than?
Oh, it's
Less
decreasing, so it's a greater than.
This one must be bigger than the next one, right? And that means it goes down, right? So what is a sub n? Left side of this. N over n squared plus 4? Yeah? That needs to be bigger than
n plus 1
n plus 1 over
n squared. Or
n plus 1 squared plus 4. Now, for those of you, I know some of you have done this, worked the problems that I asked you to work. For those of you who haven't, well, you need to, all right? I'm not going to go through this. I could, right? I could get like cross multiply and do all this stuff and try and mess with it and convince myself, right? But I want to show you today there's another way to do this that is not necessarily always easier, but it's a tool that we have in our toolbox, all right? This is the way to show something, a sequence is decreasing. This is the right way to do it. But from Cal 1, how do you show a function is decreasing? Drum roll. To say a function is decreasing means all you have to do is show. Look at a decreasing function.
The next point is smaller.
Okay, the next point. Calculus, though. Think in terms of calculus. What did we learn about in calculus? Negative slope, right? Right? This means that if I go to any point, the slope is negative, right? So a decreasing function should always have a negative derivative. Do you agree? Do you agree with that? So another thing I could do, instead of this, is to show that the derivative of x, of f of x, now I'm looking at it as a function of x because I'm taking derivative. I have to be able to look at it, the whole function. I need to show it's less than 0. When you have a positive derivative, the slope of your tangent line is like this, right? Negative derivative is like this. If your derivative is always like this, negative, then you're going down and your function is decreasing. With me? What is the derivative of this function? I'll put the function back up here so you can look at it again. This was the function rewritten in terms of x, right? What's the derivative of that function? Not antiderivative. How do you do the derivative of that function? Quotient rule, right? Quotient rule, which is the derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. And my question is whether or not this is negative or not. Is that negative? This is a question. Do you all understand that? Okay, let's clean up the top. When you clean that up, what do you have? X squared plus 4 minus 2x squared, which is really 4 minus x squared. Do you agree on top? Over x squared plus 4 squared. Is this always negative? What can you tell me about the bottom? This is always positive, right? What about the top? Is it always negative? What if x is 0? It's not, right? What if x is 1? It's positive, right? What if x is 2? It's 0, which is still not less than 0, right? Are y'all following me? But eventually it is, okay? So when x was, look, x is really our n, right? Where's our n going to start? At 1? When we plug in 1, it doesn't work. It's not negative. When n is 2, it's still not negative. But when n is 3 or 4 or 5 or 6, now this term is going to actually overcome the 4 here, isn't it? So this is true when x is greater than 2. Do you agree? Another way we could say this is that, is this decreasing? Eventually it is. So check. You have to show this, okay? I said the biggest mistake students make when they use integral test is they just set up the integral and do the integral. They never show any of this stuff. If any of this stuff doesn't work, you can't use the test. All right, so now everything verifies we're clear to use the test. Let's go ahead and do it. No questions? We haven't even done it yet. Yes, we haven't done it. So now all we've done is we've shown just that we can use this test. That's all we've done. So now that we can, I'm going to do the integral. I believe that this is the antiderivative. All right, I'm not going to go through the work. All right, you could get that on your own. And we're evaluating this where? From 1 to infinity. Now this was a limit, right? When we have these limits at infinity like this. But because we're kind of grown up a little bit now, okay, we're kind of a little more mature as math students, we can kind of think of this. What would happen if I take a huge number? Whoa, whoa. I thought that was a phone. I was like, that's interesting. If we plug a number that's really big in here, squared and add 4, that's a huge number, right? What's natural log of a huge number? So what's natural log of infinity doing? It's becoming infinite, right? It's diverging. And if I plug in 1 here, I just get a number. So what I'm getting is like infinity minus, because remember you have to do subtraction, minus something. So this has become infinite, isn't it? So this diverges. And if that diverges, what can I say? This integral diverges. Therefore, this series, and I'm going to write the whole damn thing out. The series diverges by the integral test. Now, I don't necessarily need to say integral test. if I wrote down earlier I was doing the integral test, which I don't think I did I? Didn't I do nth term test and I said it failed, right?
Yeah.
Did I write integral test down? I don't think I did. I didn't let someone reading this, right? I didn't let anyone that was reading this know I was about to run the integral test. So you should probably go up right where I said test, the nth term test failed. On the next line, put integral test. And that way, you see what you're doing is one test at a time until it works. And this is not necessarily the order that you follow, okay? No, you don't follow any of these orders. You just look at it, and after doing enough problems, you see what would probably be best first. All right, understand? Okay, that's all I'm giving you for integral tests. You're going to have to just practice some problems, all right? We're moving on to the next test, which is called the comparison test. The comparison test, I think, is pretty logical. In other words, most people understand this test. Like when I put it up here and I draw it, they all understand. So let's say that we're interested in some sequence, some series, right? That we're going to add up all these pieces. Let's say our sequence does this. All right, now we know it has to converge to 0, right? We don't know what it does. We don't know if it converges or diverges. This right here, these are our a sub n's. Okay, I did that in the black. But there's this other series where its sequence, I'm going to call b sub n, is always bigger than this one. So you tell me this. If I'm interested in knowing what that one does, right? And I tell you that the b sub n converges, the series, what can you tell me? Why?
Based on comparison test.
Yes, but think of it logically here. Like, if the
If A sub n is always larger and it's already, and if that converges, then A sub n has to converge.
yeah, because this converging means when I take this height plus this height plus this height, the red ones, and I add up all those heights, if that gets closer to a number and it's going to converge to a number, right? If all my a sub n's are smaller, then my a sub n should converge to something smaller. So it should actually converge, right? Not diverge. It's kind of like a squeeze theorem. Now, what if I said that this one, look at the same drawing here, what if I said that this one diverged?
Then it won't.
Would you have the same, would you draw the same conclusion? No, because if this one diverged and this one's always below it, that doesn't mean that this one has to diverge. Understand? What you would need for that is this. What if I draw it this way? I tell you all the black ones are above the red ones, and this one diverges. Then could you tell me that one diverged? If I add up all the red ones, and all those heights together become infinite, and your black ones are always bigger, then your black ones have to go to infinity also. So you see there's kind of like two things in action here. It all depends on how these are related. Is the black one bigger than the red one? Or is the red one bigger than the black one? And then we have to determine, the convergence and divergence. So that's what the comparison test says here. All right, so let's look at part 1. All right, so you start out with the series. This is the one we want, right? And we know this one. So whenever you're doing a comparison test, which is what this is called, you always have a series that you're interested in, which is the one that would be the problem that they give you, right? Number 20, you write down the problem. There it is. That's the one we're interested in. You're going to compare it to a series that you know. Which series? I don't know. It's up to you. But you need to know something about that series. You need to know whether or not it converges or diverges. You have to know that if you're going to use a comparison test. So let me give you an example. We have a series here. We don't know what it does, but it looks a lot like a p-series, so I use a p-series to compare it to, because I know what that p-series does. Or I look at that and I say, it looks a lot like a geometric series. I'll compare it to a geometric series I know about. So you get to choose this one, all right? So here's the conclusion. I'm going to do it this way. If a sub n is less than b sub n, and the b sub n converges, so does the a sub n. That's the picture I drew a second ago, where the red ones were on top of the black ones. If your red ones are bigger than your black ones, and the red ones add up to be a number, then the black ones have to add up to be a number. The second would be the opposite. If your black ones are bigger than your red ones, am I making sense by saying black and red here? That picture is long gone, but if your black ones are on top of the red ones, and the sum of the red ones does what? Diverges, then you can say, so does the series of a sub n's. Now there's a third part to this test, right? Let's wait on that. All right? We'll do that in a second. Let's actually, I want to take the problem that was presented a second ago. What about this as an example? Sum 1 over n squared plus 4. If I forget to put 1 to infinity, if I forget to put that, it's understood it's 1 to infinity. Kind of like when you write square root, you don't write the 2 out there. A lot of times when you see sum without the index and stuff, it's understood to be 1 to infinity within the context of what we're doing, right? These are infinite series. None of these formulas in here, in the little tables in here when they have little sums in there, you don't see n equals 1 to infinity? Okay. All right, so start running through things. Nth term test, which is the first test on that sheet. Let limit n go to infinity. 1 over n squared plus 4. This is 0, fail, right? Okay. Is it geometric? No. Harmonic? No. Not linear, good. P-series? Close, right? If that plus 4 wasn't there. How about integral test? Would you be okay with integrating this? What would you use? What would the antiderivative of that be? Arctan? You would have an arctan in here. So you could do this integral test, but you would have to show it's continuous, positive, decreasing, right, before you could use the test? That is actually fair. You could use integral test on this problem, but maybe we can use comparison test. So if I'm going to use comparison test, right, so this is kind of like maybe I have to come back to this. I don't know. I always try and avoid integral test if I can. It's just a lot of work that I have to do. What would I want to possibly compare this to? P-series. What P-series?
1 over n squared.
Just 1 over n squared. Does that seem reasonable to you? Okay, so what I'm going to do now is I'm going to do a comparison. So I'm going to write it down. I'm going to let everyone know what I'm about to do. Comparison test. I'm going to compare it to this right here. My comparison series is sum n equals 1 to